Hi, this lesson is on multiplication and division of radicals. So you can multiply and divide radicals as long as the roots are the same, but the radicand, or the expression inside of the radical symbol, does not have to be the same. So we start with multiplication. So here's our product rule for multiplication. Product rule says that if you have the square root of a times the square root of b, well, that just means that you can multiply the radicands, or the inside, and get the square root of ab. And then all radicals have to be left in simplest form, so whatever the radicand is, when you multiply, you have to make sure that that's simplified. So let's start with a few examples. Here's number 1. I have the square root of 2x times the square root of 6x cubed. So according to the rule, the product rule, I can multiply the radicand, so that gives me 12 x to the fourth. Now x to the fourth is a perfect square, but 12 is not. So I'm going to rewrite it as 4 times 3, two factors that multiply together to give me 12, but 4 is a perfect square, so that means I'll be able to simplify that. The square root of 4 is 2, so that comes out of the radical. And the square root of x to the fourth is x squared. That comes out of the radical. And you're left with 2x squared square root 3. Okay, so here's another one. We have the square root of 6a squared b to the fifth times the square root of 12a b to the seventh. So again, using the product rule, I'm going to multiply the two radicands. 6 times 12 gives me 72a squared, and a gives me a to the third. B to the fifth and b to the seventh gives me b to the 12th. All right, so I need to break down the 72 and the a cubed because neither one can be simplified as they are. 72 gets rewritten as 36 times 2. A cubed is a squared times a. And the b to the 12th is fine, so you can leave that alone. So now we're ready to take the square root of the perfect squares. The square root of 36 is 6. The square root of a squared is a. The square root of b to the 12th is b to the 6th. And you're left with the square root of 2a on the inside. All right, let's go on to number 3. So I have the square root of 5y raised to the second power. That means that you're multiplying the square root of 5y twice. And so you get the square root of 25y squared, which is a perfect square. The whole thing becomes just 5y, and there's nothing left inside of the radical. Okay, the next example is really similar. I have the square root of 2xy to the third raised to the second power. That means that you're multiplying the same radical twice. That's what you see here. That gives us the square root of 4x squared y to the sixth. And then that's a perfect square. So the square root of 4 is 2. The square root of x squared is x. The square root of y to the sixth is y cubed. So notice that your answer is exactly what the radicand was in the original problem. Same thing happened here. My answer was the radicand of the original problem. So that will always occur when you're squaring a square root. So if I said the square root of x to the seventh squared, well, that's just x to the seventh. If I asked you to simplify the square root of 2y squared, that's just 2y. If I asked you to simplify the square root of a plus b squared, well, that's just a plus b. Okay, so this is the shortcut that I just explained here, and number 3 and number 4 show you all the intermediate steps, but you can certainly use the shortcut once you get comfortable with this. Okay, so in these next examples, we're still multiplying, but this time you're going to be multiplying a radical expression times 2 or more radical expressions, so we have to distribute. Remember, with the distributive property, you just multiply across whatever is inside the binomial or trinomial. So here I have the square root of 2 times the square root of x. Remember, the product rule says that you can multiply the 2 and the x, so that gives me the square root of 2x. And then the square root of 2 times 5, well, 5 is not inside of a radical, so it becomes the coefficient of the radical, so you just get 5 root 2. Neither one of those expressions can be simplified, so your final answer is just square root 2x plus 5 root 2. Okay, let's go on to the next one. So I have the square root of x times the square root of x minus 2 square root of y. So square root of x and square root of x, remember, shortcut is just to say, well, that's just x, but the intermediate step is that it is the square root of x squared. And then when you distribute to the next one, you're multiplying the x and the y, the ones inside the radical. So you get minus 2 square root xy. And then as a final answer, you simplify the square root of x squared, that's x, minus 2 root xy. Okay, let's go here to number 3. I have 4 root y times 2 root y minus 5. So 4 root y and 2 root y, well, you can multiply the 4 and the 2. Those are on the outside. Those are coefficients. And root y is y squared, which we know becomes just y. And then to the next one, here you multiply the 4 and the negative 5, again because 5 is not inside the radical, so it becomes negative 20 root y, and so your final answer is just 8y minus 20 root y. Okay, so here's another one, number 4. I have negative 3 root xy times 2 root x plus 6 root y. Okay, so when I multiply here, the negative 3 and the 2 get multiplied to give me negative 6, and the inside part of the radical becomes x squared y. Now distribute to the next one. Negative 3 and positive 6 gives me negative minus 18, and the inside part of the radical becomes root xy squared. Now both radicals can be simplified. The square root of x squared is x, so that comes out of the radical along with the negative 6, so you get negative 6x root y. And here, the square root of y squared is y, that comes out of the radical, so your second term is minus 18y root x. Okay, so we continue with multiplication, but this time you're going to be multiplying binomials with radicals in them, so we use the FOIL method. Remember, FOIL stands for first, outer, inner, last. Okay, so we are going to multiply root x plus 3 times root x plus 7. So first term, root x and root x gives me root x squared. Outer, root x and 7, so these are the ones furthest apart, root x and 7 gives me 7 root x. Now we're on inner, those are the ones that are closest to each other, that's 3 times root x. And then last, those are the ones at the end of each binomial, that's the 7 and the 3, so we get 21. So the middle terms, the outer and the inner, combine because they are like terms. Remember, you can add radicals as long as the radical is exactly the same, so you just add the coefficients, and we also simplified square root of x squared. So your final answer is x plus 10 root x plus 21. Okay, so we go on to another foiling problem. I have 2 root y plus 5 root z times root y minus 4 root z. So first, 2 root y and root y is 2 square root y squared. Now we go to outer. Remember, those are the ones that are furthest apart. So 2 root y times negative 4 root z. So that gives me, in the second line, negative 8 root yz. Okay, now we multiply the two that are closest to each other. So those are these two. So that gives me 5 root yz. And then last, those are the ones at the end of each binomial. So that's 5 root z times negative 4 root z. So that gives me minus 20 root z squared. Okay, so there's a couple of things that can be done. Square root of y squared can be simplified as well as square root of z squared, and the middle terms can combine. So we get 2y minus 3 root yz minus 20z. And that's all you can do with that problem. The rest of the terms are not like terms, so you can't combine. Okay, here's another. I have root 5x minus 7 root x. Notice that here the 7 is outside the radical, but here the 5 is inside, so they're going to be treated a little differently. Then I have 2 root 5x plus root x. So we go to first. Okay, so the 2 stays on the outside, that's the coefficient, and the radicals get multiplied. So 5x and 5x gives me root 25x squared. Okay, now we go to outer, the ones that are furthest apart. Root 5x and root x gives me root 5x squared. The x's combine. Now we go to inner, the closest ones. The negative 7 and the 2, which are coefficients, get multiplied to give us negative 14, and inside part of the radicals becomes 5 square root of 5x squared. Okay, now we're on last. So that's the ones at the end of each binomial. So that's minus 7x squared. Okay, so a few things can simplify. The 25x squared is a perfect square, as well as the square root of x squared. These two can also be simplified because x squared comes out of the radical. So I'm just simplifying on this next line. So the square root of 25x squared is 5x. That gets multiplied by 2. So that's why the first term in line 3 is 10x. Then the second term, the square root of x squared is x. That comes out. Sorry, this is a plus. Do I have the right sign? First, outer, yeah, inner. So this one here should be a plus. And then the third term, the square root of x squared is x, so our third term is minus 14 x squared. And our last term is minus 7x. So now when we combine like terms, 10x minus 7x gives us 3x, and 1x root 5 minus 14x root 5 is minus 13x root 5. Let me just make that look better. Okay, and that's it for that problem. Okay, so there's one more. I have 2 root s plus t raised to the second power. So that means I have to expand that binomial. That means you're multiplying the same binomial twice. So I have 2 root s plus t times 2 root s plus t. All right, so now we FOIL. First, 2 root s and 2 root s gives me 4s. Remember, root s and root s gives me root s squared, which is just s. So I skipped that step. I just wrote 4s in the third line. Outer, so those are the ones that are furthest apart. The 2 and the t multiply, and then the root s comes along. So our second term is 2t root s. Inner, those are the ones that are close to each other. That's also 2t root s. And then last, those are the ones at the end of each binomial, which are both t. So t times t gives me t squared. So that's, again, our third line. Middle terms combine. They're both the same. So your final answer is 4s plus 4t root s plus t squared. Okay, so let's move on. So here we have what we call conjugates, when you have the same two expressions, except one is being added and the other one is being subtracted. When you get conjugates, things cancel. So I want to show that to you in these next two examples. So first term, root x, and root x is just x. Outer is negative 3 root x. Inner is positive 3 root x. And last is negative 9. So the outer and inner, or my middle terms, cancel each other out. So your answer is just x minus 9. So we'll do one more. This one's a little busier, but still they are conjugates. Same two expressions, one's being added and one's being subtracted. So first term is 4a, right? 2 root a and 2 root a is 4 root a squared, but that's just a. So that's 4a. Outer gives me negative 10 root ab. Inner is positive 10 root ab. And last is negative 25b. Again, because 5 and negative 5 is negative 25. And root b is just b. So again, my middle terms cancel. They are the same with opposite signs. So your final answer is just 4a minus 25b. So if you recognize the conjugates, a shortcut is just to do first and last, and you get this answer. You can skip outer and inner because they cancel anyway. Okay, so let's talk about division. So first we need to understand the quotient rule for radicals. So if you have root a divided by root b, that's the same as root a over b. So the whole thing ends up inside the radical instead of individually. So an important thing to remember with division is that a radical is in simplest form when there are no perfect roots in the radical, which that's what we've done up until now, worried about taking out perfect square roots from the radical. But in addition, you cannot have radicals in the denominator. So if you have a radical in the denominator, you need to get rid of it. And there are two skills that you're going to learn in order to do that. Okay, so first let's look at this first example. I have root 45x to the 6y squared over root 15x squared y. Okay, so not only do we have perfect roots inside of this these radicals, but I have this radical in the denominator, which is a problem. So the first thing I'm going to do is apply this quotient rule, which is to write the whole thing as a single radical. So I get the square root of 45x to the 6y squared divided by 15x squared y. So one radical instead of two. So now I can simplify what's on the inside. 15 goes into 45 3 times. X to the 6th divided by x to the 2nd is x to the 4th. Remember, you subtract your exponents. And y squared divided by y is just y. So now that I see it like the way I wrote it in the third line, all I need to do is simplify x to the 4th. So the square root of x to the 4th is x squared. That comes out of the radical, and the 3y stay in the radical. So 3y is, you can't simplify that any further, and I no longer have a radical in the denominator, so you're done. All right, let's do another one, like number 2. I have, again, two radicals, one in the numerator, one in the denominator. So the first thing I did was write it as one single radical. So I have to simplify 3x cubed y squared divided by 12x to the 4th y. Okay, so the 3 and the 12 simplify to just give me 1/4. You don't need to write the 1 there because I do end up with a variable in the numerator, but the 4 is definitely in the denominator. X cubed divided by x to the 4th, that means that you have an x in the denominator. And y squared divided by y gives me a y in the numerator. So now I have root y over 4x. All right, so I'm going to do three things in this next line. First thing is I simplify the 4. The square root of 4 is 2, but remember it's in the denominator, so it comes out as a half. Then I'm going to use that quotient rule that I talked about in the opposite direction. I'm going to rewrite root y over x as root y divided by root x, so split them up. Okay, so now I need to get rid of root x in the denominator. Remember, no radicals can be left in the denominator. So the trick is, and this will be the first trick that you learn regarding getting rid of radicals, is to multiply the numerator and the denominator by the same expression that's in the denominator, because root x, remember, we talked about this just a few minutes ago, root x and root x is root x squared, which is just x. So when you multiply the same radical twice, you just get the radicand. So that's the purpose of that technique, is that when I multiply, you will get 2x in the denominator. The 2 comes from the 1/2 in the previous answer, and root x and root x is x. And then you can combine these two because you can multiply radicals. So you get root xy divided by 2x. And so now this problem is as simplified as can be. Okay, so that leads us to formally expressing that rule, how to remove a radical from the denominator. So one way will be the way we did that here in this previous example, which is to just multiply the numerator and the denominator by the same radical that's in the denominator. So here's another example. I need to simplify 1 over root 2x. So again, that root 2x can't be there. So multiply numerator and the denominator by root 2x. So that gives me root 2x over root 4x squared. Again, if you don't want to write this step, that's fine, because root 2x and root 2x is just 2x. So your final answer is root 2x over 2x. And those do not simplify, right? You can't simplify the 2x inside the radical with the 2x in the denominator because one is inside of the radical. You can only combine radicals if they're both the same type of radical, both square roots or both cube roots or both fourth roots, but we're just dealing with square roots. Okay, let's go here on the right to number 2. I have 6x over root 3x. Again, the trick is to multiply top and bottom by root 3x. That gives me 6 root 3x in the numerator, and root 3x and root 3x is just 3x in the denominator. So remember, this is a fraction. Fractions always have to be left in simplest form. So what simplifies here is that the 3 goes into the 6 twice, and the x's cancel. So your final answer is just 2 root 3x. Okay, let's go here to number 3. This is a different type of radical problem with radical in the denominator, because unlike the first two examples, here I have a binomial in the denominator. And when you have a binomial, the trick is to multiply by the conjugate of that denominator. So in other words, I have to multiply numerator and denominator by square root of x minus 2. So you pick the opposite sign of whatever's in the original problem, and you change that to from plus to minus, and if it was a minus, you would make it a plus. Okay, so now that I know what I'm multiplying by, on the top you got to distribute, and on the bottom you have to FOIL. All right, so I'm going to distribute on the top. That's 5 root x minus 10. On the bottom, I FOILed, so I have first, that's x. Outer is negative 2 root x. Inner is positive 2 root x. And last is negative 4. Remember, with conjugates, outer and inner cancel. So if you don't want to write that step, that's fine. So you're left with 5 root x minus 10 divided by x minus 4. Okay, so you know you're done because the radical that's still in the problem is in the numerator. It can't be simplified anymore, and my denominator has no radicals and nothing else can be simplified. Okay, here's another example of that technique. I have root x minus 3 divided by root x minus 5. So the conjugate of the denominator is root x plus 5, and you multiply that on the top and on the bottom. So on the top, because I have a binomial and a binomial, so 2 terms multiplied by 2 terms, you have to FOIL. So I get first is x, outer is 5 root x, inner is negative 3 root x, and last is negative 15. And my denominator, you're FOILing as well. Again, first, outer, inner, last. If you only want to do first and last, that's fine. I wrote them all out here. So first is x, outer is 5 root x, inner is negative 5 root x, and last is negative 25. Outer and inner cancel. So your final answer is x plus 2 root x minus 15 divided by x minus 25. And again, you know you're done because the only radical left in the problem is in the numerator and it can't be simplified anymore. There are no like terms that you can still combine, and my denominator does not have a radical. Okay, so that's it for this lesson. Give the homework a try. This does require quite a bit of practice, so do it with patience. So good luck.